Hi, welcome to the Infinite Actuaries online seminar for Joint Exam 1/P. I'm David Ravel and will be your host as we learn about probability. Before you watch this video, I want to also encourage you to watch the videos in the Before You Begin section of the seminar, as they cover various study strategies, as well as answer a variety of frequently asked logistical questions. Assuming you have done that, in this first lesson I want to look at what I'm going to call the fundamental principles of probability. In some of the other textbooks on the recommended syllabus, you might see these referred to as the, quote, laws of probability, or the axioms of probability. Basically, the idea of what I'm going to do is I'm going to talk about probabilities of events, and how probabilities change as we combine events using things like unions and intersections and complements. Now, even though this is the very first lesson, we will cover enough material to see some variations on some old exam problems, and so I will end this lesson with two slightly simplified exam problems. All right, let's dive in and start. What are the basic principles of probability? Well, I'm going to start by leaving a suspicious amount of white space at the top of the page and begin with an example. In this first example, I'm going to roll a fair six-sided die. I'm going to let S denote what's called the sample space, which is just a fancy way of saying the set of all possible outcomes. If I'm rolling a die, what can my outcomes be? I can get a 1, a 2, a 3, 4, and so on up through a 6. I'm ignoring the possibility of the die landing on an edge because that doesn't really happen in the world that I live in. Within our sample space, I might have subsets that we call events. So I might have an event that I'm going to denote A, in which I roll a 3 or higher. So I roll a 3, 4, 5, or a 6. What's the probability of this event occurring? Well, if I have a fair die, then all 6 of my possible outcomes are equally likely. There are 4 outcomes that result in me being in this event A, in which I rolled a 3 or higher. And so probability of A is just going to be 4, the number of outcomes at work, divided by 6, the total number of outcomes. In particular, I got something that was in between 0 and 1. Probabilities, our first axiom, is that probabilities always have to be between 0 and 1. An event that will never occur has probability 0. An event that is guaranteed to occur has probability 1. The state space is a set of all possible values, all possible outcomes. We're guaranteed to have one of those possible outcomes occur, so the probability of our state space is 1. It's a chance of something that's guaranteed to occur. And the probability of the empty set, well, the empty set will never occur, and so that has probability 0. Now, so far these axioms don't appear to have too much content to them. Basically, all we've said is that probabilities are between 0 and 1. To change that, we want to talk about how can we combine or potentially split up events. So instead of having A be the event I roll a 3 through 6, I'm going to let A1 be the event I roll a 3, 4, or a 5. I'll let A2 be the event that I roll a 6. What is the union of these two sets, A1 and A2? Well, A1 is the numbers 3 through 5. And A6, which I just highlighted in yellow, A6 is number 6, sorry, A2 is number 6, which I'm highlighting in blue. A1 union A2, well, everything was either yellow or blue, so A1 union A2 was everything in A. What was also nice about this decomposition is everything was either blue, is either 3, 4, or 5, sorry, either yellow, 3, 4, 5, or blue, it was 6. So A1 intersect A2 is going to be the empty set. What's the probability of A1 and A2? Well, the probability of A1, there are 3 of outcomes that result in A1. There are 6 total outcomes, so probability of A1 is 3 out of 6. And for A2, there's one way that I can get something in A2, namely I roll a 6. There are 6 possible outcomes, so the chance of A2 is 1/6. And if we combine those, do the probability of A1 plus the probability of A2, we get 3/6 plus 1/6, which adds up to 4/6, which is the chance of A. And that's going to be our third axiom. If A1 and A2 have the intersection of them as the empty set, then the probability of the union is the sum of their probabilities. Notice that the first part of this equation is suspiciously in blue for no apparent legitimate reason, so I'll come back to that later on. Before I do that, though, I want to look at a second example that's a little bit more geometric and rely on some of your more geometric intuitions. Instead of picking a number from 1 through 6, let's suppose I pick a point at random from a rectangle S, where the total area of my S is 1. What do I mean by pick a point at random? I just mean each point is picked, quote, equally likely. Meaning if I have some subset A within that, the chance of picking a point within A is going to be simply equal to the area of A. In some sense, it's like the number of points that we have in A divided by the total number of points that we have. If the percentage of points that are in A is simply the area of A divided by a total area of 1, or just the area of A. Now I want to illustrate this third thing. So suppose that I have some A1 intersect A2 that's the empty set. So I'm just going to take my set A and split it in half down the middle. So the left-hand side is green, right-hand side is blue. My A1 and A2 intersection is the empty set because you're either green or blue. You're not both. You're not bleen or whatever the mixture of blue and green is. And then I could say that A1 union A2 is all of A because everything in A was either on the left-hand side that became green or on the right-hand side that remained blue. The area of A is equal to the area of the left-hand side plus the area of the right-hand side. That's just the basic way areas decompose. And so the probability of A, which is the area of A, equals the probability area of A1, plus the area of A2, which is the probability of A2. Right, this is just my second part of the equation here, of my third axiom. Now, what about this blue assumption in my third axiom? I don't really like this restriction that A1 intersect A2 has to be the empty set. It seems awfully restrictive. So what I want to do is just get rid of it. How will that change things? Well, if you're an avid watcher of The Big Bang Theory, you actually perhaps already know the answer. As Sheldon once wrote in his whiteboard, that the probability of the union is less than or equal to the sum of the probabilities. So what we're going to do if we get rid of this is if this becomes less than or equal, we're going to need to maybe subtract something on the right-hand side to rebalance this and keep it as an equality. For now, let's just take that third axiom away entirely and go back to our two examples. First, our first example, I'm rolling a fair six-sided die. Remember my sample space, my all possible outcomes were just numbers 1 through 6. Now let's change up my A. Now let's suppose A is that I roll an odd number. It means that I roll a 1, a 3, or a 5, one of these yellow numbers. What's the chance of that occurring? Well, there are 3 odd numbers from 1 through 6. So probability of A is 3 divided by 6. I'm going to be the event that I roll a 3 or less. So it's the numbers 1, 2, and 3, which I'm highlighting here in blue. What's the probability of B occurring? Well, there are 3 outcomes that result in B. There's 6 total outcomes. So probability of B is also 3 divided by 6. All right, now what about A union B? Well, I'm going to color everything that was in A in yellow, color everything that was in B in blue. What's A union B? It's everything that is yellow and or blue. 1 is in both colors, right? It's yellow and blue, so 1 is in my union. 2 is blue, so it's in my union. 3 is both, so it's in my union. And 5 is yellow, so it's in my union. So my union is 1, 2, 3, and 5. 4 and 6 are uncolored. They're not in my union. What's A intersect B? Well, that is what is both yellow and blue. That's just the numbers 1 and 3. All right, now how does this relate to my probabilities? What's the probability of A union B? There are 4 elements in A union B, so probability of A union B is 4, 6. Before, we were writing the probability of A union B as the probability of A plus the probability of B. So let's add up the probability of A plus the probability of B. Well, I have a little bit of a problem here. I have 4 equals 6. 4, 6 equals 6, 6. Because I have a little bit too much. This 3, 6 counted the 3 ways that were yellow. The second 3, 6, and B counted the 3 ways that were blue. But 1 and 3 were counted both in the first 3 and the second 3. I double counted them. So I want to subtract off the probability of A intersect B, the probability of these things I double counted. So what we get here is that the probability of A union B is the probability of A plus the probability of B. But then I subtract off the probability of A intersect B. I subtract off those things that were colored in both colors that were double colored, double counted to get the correct answer. And that's going to be my updated third axiom. The probability of A union B is the probability of A plus the probability of B. But as I told you, this was going to be less than or equal to, and as to make it a little bit smaller, I subtract off the probability of A intersect B. Let's look at this in the context of my geometric example. I had a set A, and then my probability of being in A is just the area of A. Let's suppose I have some other set B. And so I have a blue set A, a yellow set B. Their overlap, that's both yellow and blue, I'll color in green because green is what you get when you mix blue and yellow paint. What's the area of A union B? Well, it's simply the area of A plus the area of B. So that's area of A is everything in blue plus the green stuff. Area B is everything that's yellow plus the green stuff. That green stuff was double counted. It's counted here and there. So I need to subtract off the area of A intersect B to get the correct answer. And then these are just probabilities. That's simply the probability of A union B equals the probability of A, the probability of B, minus the probability of the intersection, just like my third axiom. And now let's take a look at a key special case, namely that of complements. Suppose I have a set S, that's my state space, and I have some set A. I'm inverting my colors from what I had before. So before I had a white state space, and my set A was colored. Here my set A is white, and everything outside of A I left colored. Because what's outside of A is what I want to focus on. It's what I'm going to call A complement, which will denote usually with an A prime on the exam. Sometimes people will denote it as A superscript C. That is called A complement. It's the set of everything that's in our sample space, but not in A. It's everything else. The point is that A intersect A prime is the empty set. You're either in A or you're in A complement. You're not in both. And the union is equal to sample space because you're either in A or you're in A complement. For example, suppose I rolled a pair of 6-sided die, and A was my very first example in which I rolled a 3 or higher. So my sample space was 1 through 6. My set A was 3, 4, 5, and 6. A complement is everything that's in S that's not in A, is everything that's not colored here. So A complement is just this blue stuff, namely the elements 1 and 2. How does this relate to probabilities? Well, the intersection is the empty set, and the union is the whole space. So probability of A plus the probability of A complement equals the probability of the union because there's no intersection probability to subtract. And the union is the sample space, which has probability 1. So probability of A plus probability of A complement add up to 1. Probability of A complement is therefore just 1 minus the chance of A. And we can actually do it the other way around. I could have subtracted probability of A complement from both sides to get probability of A is 1 minus probability of A complement. Another mathematical way you could see is what is a complement of A complement? A prime is the blue stuff. A prime prime is everything that's not blue, namely the white stuff. So it's just A. Right? And so if you just reverse A and A prime, you get the probability of A is 1 minus the probability of A prime. Now suppose that we add on a second set B that overlaps. What is everything in B? Some of the stuff in B is sort of this lighter stuff that's in both B and A. Some of the stuff in B is the darker stuff that's in both B and A complement. So we can think of B as being A intersect B, the lighter part of B, plus the stuff that's darker, the A prime intersect B. So B is equal to that union, and those you're either in the light colored part, A intersect B, or in the darker colored part, A prime intersect B. You're not in both, so the intersection is the empty set. So that tells us the probability of B is the probability of A intersect B plus the probability of A prime intersect B. This is a special example of how to take an event, namely B, and break it down into smaller events, A intersect B and A prime intersect B. Later on, I'm going to generalize this to something called the law of total probability, but we'll see that not for a few lessons. All right, now let's take a look at an example. Every time we look at an exam-style problem, I will encourage you to pause the video and try to work the example on your own. The best way to learn math is through doing it yourself, by pausing the video and doing these examples on your own. You can find blank copies of the examples in the lesson handouts PDF. I will also indicate these suggested pauses partly by verbally telling you to pause, but also by that page flip icon that we just had. Right, we have this little page flip animation right here as we're encouraging you to pause. So here's a variation of an old exam problem. So I encourage you to pause the video and try it on your own. Are you all ready to resume? What do I have here? I have a visit to a primary care physician's office. I might have lab work or a photo to a specialist. So first thing I want to do with a word problem is introduce some notation. I might have referral lab work. I might have referral to a specialist. I'll let L denote the event that I require lab work. And I'm going to let S be the event that I end up getting referred to a specialist. Now, the things I've highlighted in color in the example are all the clauses, all the pieces of a sentence that contains a number. Every one of those will give us a fact that we'll have to plug into some sort of equation. What's our first number? Our first blue equation is either lab work or referral to a specialist is 60% probability. So probability of L union S is 60%, 0.6. The green sentence says the probability of a specialist referral, which is S, is 35%. So probability of S is 0.35. And the purple equation says the probability of L is 0.5. I want the probability of L intersect S. Right? I want the probability that results in both lab work and referral to specialist. Ands tend to mean that I want to do an intersection. Ors, like we had in the blue, tended to give us a union. So I want the probability of L intersect S. Do we have any formulas that connect intersections with unions? Well, yes, we do. It's the only formula actually that we know so far. Namely, the probability of L union S is the probability of S plus the probability of L minus the probability of the intersection. And I just plug in these numbers. Probability of the union is 0.6. Chance of S is 0.35. Chance of L is 0.5. The last term is what we want to solve for, so I don't know it just yet. But now I just have a linear equation with one variable, probability L intersect S, and I solve and I get 0.25. Now we have another page flip. So again, this is another exam style problem that you should pause and try to work before you resume the video. And again, if you want a clean printout of this or any of the other examples that we do, see the A1 examples PDF handout. All right, so how do we do this one? Again, we have a word problem. So again, we want to translate everything from words into symbols. We're talking about visiting a physical therapist and talking about visiting a chiropractor. So let T be the event that we visit a physical therapist and C the event that we visit a chiropractor. Our first sentence, 25% visit both. So I'm a physical therapist and a chiropractor. That's an and statement, so it's an intersection. Probability T intersects C is 0.25. 85% visit at least once. That means a therapist and or a chiropractor. That's a union, right? At least one means a union of the two. So probability T union C is 0.85. Probability of a chiropractor exceeds by 0.2 probability of visiting a therapist. So probability of a chiropractor is 0.2 plus probability of a therapist. What equations do I have that connect unions and intersections? Well, it's our usual one. Probability of the union is the probability of one plus the other minus the probability of the intersection. And now I just copy down my numbers. Probability of the union is 0.85. Probability of a chiropractor, I want to find the chance of visiting a physical therapist. So I'm going to write everything in terms of P of T. So probability C I don't know, but I know it's 0.2 plus P of T. P of T is what I'm trying to solve for. And the intersection is 0.25. So again, I solve for P of T and I get a final answer of 0.45.